this afternoon by Parzanchevski. And you can see his title up here. And of course, we're in the Bay Area, so this is very appropriate.
That's where it comes from, so okay. The name. So. Thank you very much for the invitation. It's great to be here. I will tell you about, Ramanujan Graphs, which actually don't appear in the title because I already had too many objects to put here. And the recent developments around them. So what are Ramanujan graphs? You should all know that a K-regular graph is an expander if the non-trivial eigenvalues of its adjacency operator are small. And trivial, non-trivial, for that we say what is trivial. Trivial is the constant eigenfunction or an eigenfunction which is constant on a bipartition of a graph. And so this is the non-trivial. And the other question is, what is small? How small is small? And there is an answer, which is due to Alon and Bopana, which is the best one can hope for is the spectrum of the tree. So this is as small as you can get. So this is the spectrum of the tree, of the K-regular tree. And we're trying to get to find graphs which have this concentration of the spectrum. So a K-regular graph is Ramanujan, and we heard it several times, if the non-trivial spectrum is contained in this interval. Now, every K-regular graph is a quotient of the K-regular tree by some group of isometries acting on the tree. And what Lubotsky, Phillips, and Sarnak did in the 80s was for prime p, which are congruent to 1 mod 4, they gave the p plus 1 regular tree an arithmetic structure, which is something I will explain in what follows. And they did it with a philosophy in mind coming from number theory, which is that if you have a geometric object, its arithmetic quotient behave nicely. And in this case, it gave them Ramanujan graphs. So I will tell you a little bit about that and about what they did exactly. And then I will explain how it resurfaced suddenly in the area of quantum computation in recent years. And then I will tell you a little bit about the recent construction in joint work with Sarnak. And if I have time, then I'll tell you a bit about what happens in high dimension, which is high dimensional expanders, which people already mentioned a bit, but I don't think anyone actually talked about so far. So first, let me recall what is a unitary group. So I have a ring R, and I look at the unitaries, 2 by 2 unitaries, so matrices in the ring, not R, but R when I adjoin I. I is the square root of -1. And I look for matrices such that A star A is the identity. And star means that I take the transpose and conjugate. So take I to -I. These are the unitaries. So if I take for R the reals, I get the unitary matrices you know from first year, linear algebra. But think about other rings as well. Think about the integers or even finite fields. And you can do it the same for any ring you like. But it's nicer to look at a tiny bit different group, which is the group of similitudes. So I take, again, matrices in the same ring, but now I allow A star A to be also any scalar matrix, not only the identity, any scalar, as long as this scalar is invertible in the ring. When I do this, it's suddenly very strong. And eventually I mod out by scalars. So this is a projective group. I don't care about the multiplication by scalars. So for example, if I do the same, this for R, for the reals, I get the projective unitary groups. So the fact that I allowed here a scalar doesn't matter, because if A star A is lambda I can always scale A by the square root of lambda, and I get a proper unitary matrix. So for the reals, it doesn't matter. I get the projective unitary, but I can't do this square root over any ring. So sometimes it will matter a bit. The ring which we will look at for most of this, the next half hour, is Z1 over 5, which is all the rational numbers with denominator equal some power of 5. And here is an example. This is a matrix, and it belongs to the unitary similitudes over this ring. Why? I take the matrix times its star, the conjugate transpose, and you can check that you get 5, 5. You get a scalar matrix, and the crucial point is that 5 is invertible in this ring. So what you should think about is that this R here allow me to clear denominators. I don't need to divide by 5. I can multiply everything by 5. So think eventually about this ring, about this group, as all the matrices in the Gaussian integers, because I can always clear the denominators, and which have this property that A star A is some power of 5. And feel free to ask questions. And here is a theorem, Lubotsky, Phillips, and Sarnak, showed that if you take these 3 matrices, so this is the one we saw, and these are 2 others that are also in the same group and also appeared before lunch, if you still remember, on the whiteboard, they generate a free group. So this is not trivial. And another question which is not trivial is which group do they generate? Do they generate this entire group, for example? And the answer is no. They generate this. They generate the subgroup, so all the matrices, which in addition to this condition are congruent to the identity matrix mod 2. So if you look here, you see this 1, 1, 1, 1, 1, 1, and all the other things are congruent to 0 mod 2. So if you multiply 2 matrices like this, they will still be of this form, but you get everything of this form. And because it's a free group on these generators, this tells you that the Cayley graph of this infinite group with respect to these generators is a tree. So this is a tree. A Cayley graph of a group is a tree if and only if the group is free on these generators. And what they do now is take, I call this gamma 2, and gamma 2q is the same thing. I put here 2q, where q is any prime. And I get a subgroup of gamma 2, because if you're congruent to identity mod 2q, you're also congruent mod 2. So this is a subgroup, and it's a subgroup of this group, and we're looking at the tree, which is the Cayley graph of this group. So we can divide the Cayley graph by the subgroup. This is what I meant earlier by arithmetic quotient. We found a way to present the tree as an arithmetic group, and we're taking an arithmetic quotient of the tree. And this is the LPS Ramanujan graph. You take the Cayley graph and you mod out by a subgroup like this for some q. This is the famous LPS graph. And you can say a bit more. Actually, you can observe that this is actually even a normal subgroup of this guy. So if you divide the Cayley graph by a normal subgroup, you get the Cayley graph of the quotient group. So actually x5q is the Cayley graph of the quotient group, gamma 2 mod gamma 2q with these generators. And you can work a bit harder to show that actually this group is someone you know. This is PGL2FQ or PGL2 or PSL2FQ. It depends whether 5 is a quadratic residue mod q or not. And this is how you usually see the statement. So usually people start from the end, from here, and build the Ramanujan graphs, but I think it's the other way around. And the proof uses very deep results from number theory, Ramanujan-Peterson conjecture, due to originally what they needed was due to Eichler, but the most general thing is Deligne, and the functoriality of Jacquet and Langlands. I won't get into any details about that. And I'll say a word what happens for general P. So until now I did everything for 5, but what they did apply to any prime which is congruent to 1 mod 4. And what they do, they apply Jacobi's 4th square theorem, which tells you that for primes of this form, there are 8 p plus 1 solutions to this. So 8 p plus 1 way to write p is a sum of 4 squares. And for each solution like this, you can get a matrix like the one we want. You take alpha equal a plus bi, beta c plus di, and then you put alpha beta, and you complete it to a unitary matrix by adding minus beta bar, alpha bar, and you get a matrix which has this alpha star alpha equal p. Now, among these solutions, exactly 1/8 are congruent to the identity mod 2, so you get p plus 1 solution with this additional property. We call them SP. And here is, for example, S5, what we saw earlier. And what they show is that for any p, which is 1 mod 4, you get a regular tree. So you get a free group. And this is where the LPS graphs come from. So later it was done, the same was done for p equal 2 by Q. And Davidov, Sarnak, and Vallet in 03 did the same for the rest of the primes, which are 3 mod 4. Questions? Okay, so how did this resurface lately? So now I'll tell you everything that I know about quantum compiling, and it will take me one slide, which even begins in the middle. So a qubit, as far as I understand, is an element in C2 mod scalars. So it's a vector of 2 complex numbers, but I don't care about scalars. I can multiply both coordinates by the same scalar. And in the quantum computing world, this replaces F2 in the classical world. So our computers work with bits, and this is what quantum computers will one day work with. And the quantum gates are the logical gates that you can apply to these entities. So for F2, for example, you have actually 4 gates that you can apply to a bit. You can do identity, not constant 0 or constant 1. There's not much you can do with 1 bit, right? But if you have 1 qubit, you suddenly have the whole of PU2. So the unitary matrices, the projective unitary matrices on C2 act on this thing, and this is what a quantum computer should be built from. So this is the model of a quantum computer. And so this is uncountable, unlike here that we had 4 gates. So already to understand how to build quantum gates for a single qubit is quite hard. We can't implement all of PU2. As I said, there are uncountably many elements here. So what we're trying to do is find gates, so a finite set of gates, which topologically generate PU2. So I want this thing to generate a group which is dense. So at least I'll have something which approximate any unitary operator here. So this is the basic problem in modeling quantum computer on 1 qubit. But we want to do better. So a bit harder, or could be much harder, is to find efficient gates. So by efficient, I mean I don't want these AIs only to generate PU2. I want them to generate it efficiently. So for any matrix I give you, and I tell you some epsilon, I want to find a matrix in the epsilon neighborhood of M, but I want this matrix to be a short circuit. So I want to have a short word in the AI, which is epsilon close to this M. And then you can work out what is short. And usually you want to compare yourself to the random. Random is always good. So you say, okay, how many circuits do I have in AI? Let's say I built R quantum gates, and then I look at a circuit of length 10. Then I have R to the 10 circuits. Let's say all these R to the 10 circuits were distributed completely randomly in PU2. Maybe even not even randomly, but really as a lattice packing. I would like to compete with that.
Is a circuit a word?
Sorry?
A circuit is a word?
Yeah. If you're a mathematician. I thought you weren't. You would say a word if you come from mathematics, or circuit if you come from engineering? I don't know. How do you say circuit?
More complicated. But
Sorry?
usually by circuit you mean something more complicated than just a word. But
Okay, yeah, but I think this is the word at least some of these people use. I like it. So short would be similar to random. So and we know random is always good. You could like take random gates and they would distribute nicely. The problem is you want to build your gates and you can't always every time you want to compute something build new gates. You want once and for all build this gate, a finite set of gates, and then you want it to generate a pseudo-random group.
Actually, if you're going to care about the length of this short, what short means, then it's important, as Noga said, to say it's a word and not a circuit. A circuit is what is called a straight line program also. And this is a straight line program. You are allowed to generate more elements and remember them, and then use them in the computation.
Okay, no. I only think about the product.
So these are short words. Products is
short words.
So you like it, but it's
But I don't know what it is. Yeah, that's true. Okay, so this is harder to find efficient generators, and even harder is to actually find this circuit. So let's say I have these generators and I know that there is an M in an epsilon neighborhood. How can I find this M and then to decompose it as a circuit? And this is what Nasser was talking about for the last hour. And another thing which is nice to have is a good growth rate. So if I have a lot of algebraic relations between my gates, I'm losing something. If one of them cancels another one, then I get less circuits, less words than I would like to. So the nicest thing would be if these AIs would have no relations, and then I would really have R to the L different circuits of length L, words. Okay, how does this relate? So this is what Peter Sarna calls golden gates, and it really happened because he first gave a talk about it, I think, in Stanford. So he had the golden gate in mind. These SP, so I remind you, the SP were the LPS generators in the unitary group over this ring. But this ring is a subring of the reals. So this generator sits in PGU2R, which we said is actually PU2. And this is the group of unitary transformation or gates on one qubit. So it actually sits there. And I can look at the group they generate. We call this gamma 2. And this is a free group which sits inside PU2. So free group is good. It means I get as many circuits as I want. Not completely, okay. And this was carried out in the paper of Bocharov, Gurevich, and Svor. They realized that they can use this thing to build what they call V gates. V comes from the 5, the fact that this has to do with 5. And they analyzed how good these gates were for quantum computation. So the growth rate is really good. It's not 6 to the L because you have here inverses. So you get only 5 to the L circuits because for every matrix you also have its inverse. But it's very good. And we can do the compiling nicely. So here's a matrix. It's very easy to check that it's in this ring. So you can compute M star M. You get 5 to the 11. And M is congruent to 1 mod. This should be 2. And this tells me that this sits in, this is by LPS, this sits in the group spanned by these matrices. So there should be a word. And then you can actually find this word because this is a tree. These things span a tree, and on a tree we know there is a unique shortest path between any 2 points, and you can compute it. And they do that thing here. And what is harder, as I said, is to go outside this group. So now I have a general point in PU2, and I want to find a closed point in this subgroup. And this is Ross-Selinger, and Nasser did an analog thing over the p-adics. So this is I talked about compilation and about growth rate. I didn't talk at all about efficiency.
Do you want just growth rate, or do you want these words to be somewhat far apart?
That's the efficiency. So that's the next slide. So I want them to be efficient. How efficient are these gates? So for that, I wanted to imagine, again, an expander. But this expander I want to think about the Cayley graph of PU2. So this is an uncountable group. And these are these finite set of matrices. So think about the 6 matrices we saw earlier, and take the Cayley graph. So this is an uncountable graph. Of course, it's disconnected. Every connected component is countable. But I connect every x to Sx for every x in Pu and S in this generating set. So from every matrix, I have 6 edges going out, corresponding to these 6 elements. And I want to think about the spectrum of the adjacency operator. So if I would just think about the adjacency operator, this is very disconnected. It's not an expander in the classical sense. But I need to put in the topology. So we look at the adjacency operator, but acting on functions which understand the topology of the unitary group. So I actually think about continuous functions, but the literature usually talks about L2 functions. So think about adjacency acting on L2 functions on the space. And the adjacency is, again, for every point, you sum the translation by the elements in the set S5. SP. And you get a P+1 regular graph, uncountable and everything, but P+1 regular. In particular, if you take a constant function, you'll get, and you apply the adjacency, you're summing P+1 translation of this constant function, you'll get the same thing times P+1. And I would like to say that what we know about expanders works. So if SP topologically generate PU2, then I would like to say that if I apply the adjacency and get my original function times the degree, it means that my function is constant. So at least for continuous functions, it works. So think about a continuous function. You know that on a connected component, if it's k regular and it satisfies this, it means that it's constant. But if your orbit, if your connected component is dense and the function is continuous, then it means it's constant. And this suggests that, okay, it should behave the same. If the other, so k tells me that I'm disconnected. So if everything is far away from k, I should be very connected. I should be pseudo-random. And indeed, it is so. So there are 2 papers, Hecke operators and distributing points on the sphere part 1 and 2, written by Lubotsky, Phillips, and Sarnak in 86 and 87. I think they were written after the Ramanujan paper, but probably appeared much earlier, because if you ever send something to Combinatorica, you know how it goes. They show them there are a few things. If you define lambda s to be the second largest eigenvalue of this adjacency operator, so I sum this translation by s, and I look at the second largest eigenvalue, and they really show that if this is small, so far away from k, then your set generates efficiently the group, so it gets fast everywhere. By this I mean that for every L, the circuits or word of length L in the generator distribute pseudo-randomly. So they look similar to what you would get if you would distribute points randomly. And they have an Alon-Bopana bound, which is if you have any set of elements, with finite sets, size k, and it's symmetric, so it contains the inverses of every element there, then lambda s is at least 2 square root of k minus 1. So here there's no as something goes to infinity, because somehow this L2 PU2 has already this going to infinity thing. And what they show is that their generators achieve this Ramanujan bound. So this is exactly the bound you get for the k-regular graphs, and this is a k-regular graph, but in topological settings. And they can do it with the same generators. So it looks really, really similar, but the proof is much harder. So it's not that you do this, you copy word by word. It comes from the same ideas, but it needs more than what you need for the Ramanujan graphs. Yeah, so proof uses even more number theory. But this basically tells you that the quantum gates you get from LPS graph, for LPS generators, are good. And really, in some sense, as good as you could have. So like Avi said, in the spectral sense, you could do other things. Now, if you open a book about quantum computation, you'll see that the business today is run by the Clifford+T gang. So people don't use the LPS gate, they use these guys to model quantum computation. And C is called the Clifford group. It's a group of size 24, isomorphic to S4. And T is another gate, this gate. And this is what people use to model quantum computation. And it was not that long ago shown that this group also arises in arithmetic setting. So Kliushnikov, Maslov, and Mosca showed that the group generated by C and T together is exactly the entire unitary group over Z when you add the square root of 2. So it means that you can do similar things. And so, okay, one question is, why is this better than the LPS? And they have a very good answer, because you can implement these gates in a fault-tolerant way. So for any computation, you would like to have fault tolerance. And there is a protocol or algorithm of Shor and Kitaev to do quantum computation with fault tolerance. But you need, for that purpose, all your gates to have finite order. So all these matrices have finite orders, both C and T. And you don't have that for the LPS. We saw that LPS generate a free group. In particular, all the elements are of infinite order. But this also has a big disadvantage in terms of growth rate. The growth rate is really not good. I'll show you that in a moment. And what we did recently, so this is the joint work with Peter Sarnak, is to construct efficient and fault-tolerant gate. So where do they come from? A basic point in the work of Lubotsky, Phillips, and Sarnak is to show that these groups that we got act simply transitively on the vertices of a tree. So this is one way to show that a group is free, to show that it acts simply transitively on a tree. Everyone know what simply transitive is? Yes? Like for every 2 vertices in the tree, there is a unique element in the group which takes me from this vertex to this vertex. And this tells me that the group is free. So this is Sayre, I don't know. These are classical results. And what we do is we find arithmetic group which acts simply transitively not on the vertices of a tree, but on the directed edges of a tree. And here's an example. So this is a group generated by 3 elements. And it acts simply transitively on the edges of a 3-regular tree. And it sits inside the group generated by Clifford+T. And it sits there as a subgroup of finite index, which tells you that the growth rate is the same. But here we have 3 elements, and here you have 25 elements. So it means here you're really wasteful. You look at 25 to the L circuits, but actually your growth rate is only 2 to the L, because you can do it with 3 elements.
What are the orders of these elements?
What?
These elements are finite order,
Yeah.
which one? What order?
What are the orders?
Yeah.
So this is 2, and these I think are 3.
These are what?
I think it's 2, 3, 3. I think. But you can multiply a matrix with itself and see when you get to the identity. Yeah, it's a 3 regular. Okay, you'll see that in a moment, what it is. So what we have a general idea of how to construct these things, and it's the following. You want to find a C and T. So it's misleading because these are not the Clifford+T, but we kept the same notations inside the unitary group, which acts on a tree so that the group C fixes a vertex. So there is a vertex which is fixed by the finite group C, and C acts simply transitively on the neighbors of this vertex. And T flips an edge. So T should be an element of order 2, which flips an edge which touches this vertex. So here an example. This is my basic like fundamental origin vertex, and this is an origin edge. And T flips this edge. So this is E0 and TE0. And C takes this E naught to the other edges. So here's one C E naught, C prime E naught. And I can also flip and then rotate. So I can take T and then some C, and I get an edge going inward. Or I can rotate and then flip, and I get something here going outward. And I can continue. And if you have these two things, then it's pretty easy to show that the generated group acts simply transitively on the edges. And it's fault tolerance because C is a finite group and T is an involution. It's order 2, so they're all a finite order.
So can you say a word what you mean by fault tolerant? Just finite order?
No. I don't know how Shor and Kitaev do this. I know that they have a way to compute with some redundancy. If all the generators are of finite order, they compute somehow more, and eventually they can...
That's the only assumption, just finite order.
Not the only one, but it seemed to be the crucial one. So it's not that I know that for any gates of this form you can implement anything, but this is what we guess.
Some of which looks that if the orders are small, then you lose something in the growth rate, maybe, right? Because they are short relations.
So I'm not getting into details, but there is some assumption that C costs you nothing to implement, which is they always assume that.
No, he's talking about just the word length.
Yeah, so actually they always talk in terms of the T count. They don't care about C. Like C is cheap, T is expensive. So it's an industry. We can talk about it. Sure. Okay, so all of them are of finite order. So hopefully we can implement them in a fault-tolerant way. And under this assumption, this gamma is a free product of this C and T. So there are no relations between the T and the C, which means that you have an optimal growth rate under these assumptions. So if you want C to be finite and T to be an involution, this is the best you can do. And finally, you can navigate. So earlier we were working on vertices. Now we're working on edges, but I know now how to flip an edge and how to rotate. So I can flip and rotate and flip and rotate and get from everywhere to everywhere in a unique way. Now, what about efficiency? So what about expansion? So look again at this picture. And I'm going to look at the set. I'm going to take as my S the set of elements of the form TC, where C is not the identity of C. So these are the green elements, because each C here rotates me, and then T flips around this edge, so it will take this guy somewhere here. Now what happens if I do that again? I take some C, so C rotates around this edge. So from here I'll get somewhere here, and then I flip again. I'll get something here going out. And every time I do that, I progress, but only in that direction. You see that? And what happens is that when you apply powers of C, you're actually getting a non-backtracking random walk starting from this directed edge. So you're always going forward. And this already tells you that these elements generate a free semigroup. So there are really no relation, not even inverses. And a free semigroup has really the optimal growth rate, even better than a free group. It really is S to the L. And somehow it's not clear why people always assume that everything is symmetric and that everything is grouped. In terms of, like, if you want to actually build a quantum computer, you would need to implement the inverse. But you can not implement the inverse, and then you have a better growth rate because you don't have this relation. So here, this is optimal. And okay, I didn't tell you where we get these gates from, but they come again from arithmetics, and we can use the same machinery of the Ramanujan conjectures and Jacquet-Langlands and obtain this bound. So this is similar to what we had earlier, but this is not 2 square root of k minus 1. This is k square root of k minus 1 without the 2. And this would be, it's k minus 1 if k is the number of vertices here. I didn't say what k is. Yeah, k minus 1.
Oh, which is equal to this.
Yeah, because this is the size of S. And the reason is why this square root of k minus 1, this is again the Ramanujan thing. I'm competing with my universal cover, the K-regular tree. But now I'm doing a non-backtracking random walk. This is the spectrum of the non-backtracking random walk on the K-regular tree. This is the second eigenvalue there. So because I'm not taking a symmetric S, I can beat the Alon-Bopana bound by a factor of 2. You pay for that somewhere else, but I won't talk about that. So it's very efficient. And it's also harder to construct than the LPS. We don't have, I think we can prove that that there's only a finite number of such gates. And this is what we think is the best. So this is, Peter called that super golden gate. This is C, a finite group. What?
Platinum.
Platinum? So this is a group of order 60, isomorphic to A5, and this is T. And we use here the golden ratio. And it acts simply transitively on the C acts simply transitively on the origin of a 60 regular tree, and T flips an edge. And we think you can't do better. In some sense, the icosahedral, this is Klein's icosahedral group, which is the biggest group you can put in U2, etc. And if you want to know where it comes from, this is almost this group. So PGU2 with Z and the golden rate, and you add the inverse of Z plus 5 phi. But actually, it's a finite extension. It's even a bit larger. And this thing comes where this 7 plus 5 phi appears when you factorize 59 over the golden ratio. So this is a factor of 59. And OK, for those who are versed with the history, this thing is actually this group is the full S plus 5 phi arithmetic group in the ring of Icosians. So this is a ring that several mathematicians discovered. It's a subring of the quaternions, which is composed of certain golden integers. And it has very rich history. So Tietz found very interesting properties of it, and Conway. And we think this is the best you can do in these settings. OK, so this is what we were doing with PU2. Now I want to talk a bit again about Ramanujan graphs. So we started with the discrete world, which we started with graphs. And then we moved to PU2. And then I gave you a new construction. And I want to see what it gives us in the old world, in graphs. So what we did now is we identified the edges of a tree with an arithmetic group, not the vertices. And on the edges, I have this set of generators. And the Cayley graph of these generators behave like the edge D graph of the tree. So by an edge D graph, I mean you have a graph, and then for every edge in the graph, you put 2 vertices, which correspond to the 2 directions you can assign to the edge. And then you connect things in the new graph if they describe non-backtracking walk. So from here I can go here, from here I can go here, but I can't go from this one to this one because that would correspond to backtracking. So this is what I mean by the edge D graph. And now I can describe the non-backtracking walk on the tree by an arithmetic group, by the adjacency operator in this group. So we have the spectrum of the non-backtracking random walk on a Ramanujan graph or on a K-regular tree, which is always inside this. So you have the trivial eigenvalues plus minus p, and everything else, like we said, is in absolute value smaller than the degree. And now I have complex eigenvalues because this is not a symmetric operator anymore. And we call a graph, a D graph with these properties, a Ramanujan Digraph. And you'll hear about them, I think, tomorrow from Alex and from Eyal. They appeared in another work we did together. And what we get from this work is that we can take our lattices, our groups of golden gates, again, take these gamma q, which are the subgroup coming from arithmetics, divide the Cayley graphs, and we get Cayley Ramanujan digraphs. So digraphs which are Cayley, so coming from a group, and they have this property of the spectrum, what we call Ramanujan digraph. And for me, this was very nice just because it allowed me to test everything that we do. So now I can actually take a group, compute this generators that we get for the group. So this is PSL2F13.
Always bipartite.
What?
You always bipartite, just plus
No,
minus.
it's contained. You could have minus p and you could...
You don't want if it's bipartite or if
No, here it's always bipartite. So here's an example, which is not bipartite. So this is what I get for PSL2F13 with 3 generators which coming from our gate. And it's really, it does what it should. I have that trivial eigenvalue at 3, and everything else is within square root of 3. So for me, this was a confirmation that we're not talking nonsense from some point onward. Here's another example. For F17, I have a bipartite one, so I have also the minus 3.
But I don't understand. Is it the same as just the calligraphing Ramanujan?
Yeah, of the line graph.
Yeah.
Yeah, so this is like you could ask for a Ramanujan graph whose line digraph is a Ramanujan digraph. Yeah. This is what we get. Okay, so I have like 2 minutes. I'll say a word about higher dimension. What happened when you try to generalize all these things higher? So instead of Ramanujan graphs, you get Ramanujan complexes, which is something I hope someone will talk about here. And just the basic thing is to understand what Ramanujan complexes are. The first thing you need to do is understand what do you replace the tree with. So this is what you get when you replace the K-regular tree with a Breuer-Titz building. And Breuer-Titz building are infinite contractible simplicial complexes, and when in dimension 1 they really are trees. So infinite contractible simplicial complexes of dimension 1 are trees. In higher dimension it's something else. And then the Ramanujan graphs are quotients of the tree which behave like the tree in terms of the spectral theory. And here's the same thing. Ramanujan complexes are quotients of the Breuer-Titz building which behave like the buildings in terms of the spectrum. So you can ask everything about them. And in the side of the quantum gates, you replace PU2 by PUN. You can go to general unitary groups and do the same thing. And you have, again, the same story for everything appears both here and here. But it's more complicated. So first, once n is 5 and above, you have no arithmetic free groups. So this is due to Kashdan property T. And also, there are no simply transitive actions in dimension 8 and above. This is due to Mohammadi and Alireza Golsefidi. Who was here earlier? So you need to work hard, but we can already do some very nice things in between. So we have this, only in low dimension we can have all these miracles, but in dimension 3 we already have everything we want, and we're trying to do the same in dimension 4. So for U4 it would be very nice because from U4 you can already construct all quantum gates. It's universal in some sense. It's like the NAND in the old world. And you can do compiling by by navigating on the building. What is harder is the approximation problem. And I say much harder, I mean that we don't know almost anything about that. We don't know how to do approximation problem. Everything Nasser told you about, we have no analog of that in higher dimension. And I wanted to show you some pictures. So I'll just show you some picture of what happens when you go in high dimension. So things become nicer graphically, but more complicated in terms of understanding. And
Any more questions, comments?
So if you start from any Ramanujan graph and you take the directed line graph as you did, it's always good.
It's
right?
always a Ramanujan digraph. That's
It's just always.
yeah. There's an old result of Hashimoto in the Hara, which tells you what the spectrum of the line graph is in terms of the spectrum. So like, So if you know how to build one Ramanujan graph, you know how to build a Ramanujan digraph, but there's no reason for it to be Cayley. This is why.
Avi?
Do you know of any case where in quantum algorithms you need more than, when you need really to approximate all of PU2? I mean, it seems that all algorithms are...
You only need diagonals.
Yeah, you need roots of unity.
No, but I'm not the person to ask.
No, maybe you're not the person to ask because somebody asked you before and you had to go and look.
No, but the thing is, as Nasser told you, for diagonal elements in U2, we have like optimal algorithm, but in high dimension, even for diagonal, nothing.
Anything else? Okay. We'll start up again in 8 minutes.